Hi students, in this clip we will discuss about the magnetic field on the axis of a circular loop or a current carrying loop. So I have just taken that proper word that is called as on the axis only because of I want to correlate this expression with the another expression which we have learnt in chapter number 1. It is called as a electric dipole moment. But first of all, let's understand this geometry. I have just shown that current carrying loop which is containing small segment dl, and from that this dl part our current I is passing. So you can just apply thumb rule which is giving me the direction of current, and this is called as a magnetic field B. So I have just shown that angle that is called a perpendicular angle. This is called as x component and it is making an angle of a theta. So as per my notation I have just this much angle is also theta. I want to correlate this expression, and this is the circular loop from let's say center to some point, let's say point P. I want to find it out my magnetic field at this point P, and that capital R is my radius of this circular loop. So first of all, before going to prove this expression, I want to prove that initial formulas which I have already proved. So dB is equals to, we have a mu 0 I divided by 4 pi into dl upon r square. But you can just see that my r is called as hypotenuse, which contains a square part, and this is making an angle of x component. So first of all I am placing that r equals to x square plus r square, and I can just say that from the figure cos theta is equals to, I have r divided by small r, so I have r under a root of x square plus r square. So those data which I am in need of, I have placed this such type of data. So I can just say that this is my x component, that is called as a dB cos theta. This expression is ready, so I am placing its values. dB of x, dB's value is called as a mu 0 I divided by 4 pi into dl. R square means x square plus r square into cos theta is called as r upon under a root of x square plus r square. What I am doing is that simplifying integration of dbx is giving me mu 0 I upon 4 pi x square plus r square raised to 3 by 2 r, and then integration of dl. But you are aware that integration dl is called as L, and we are aware about that 2 pi r for n number of loops. So for n number of loops my L will become 2n pi r. So I am placing all those data over here. So integration of dB is giving me such type of expressions, that is called as a B mu 0 IR upon 4 pi x square plus r square raised to 3 by 2 into 2n pi r square, because this r is already there and 2n pi I have placed that over here. So this is the first segment. Apart with that, you can just cancel out 2 pi and 2 pi. So my expression will become B is equals to mu 0 in r square divided by 4 pi and x square. Sorry, it would be a 2 pi or only 2 x square plus r square raised to 3 by 2. So whichever formula is convenient to you, you can just find it out this expression. So these are the two expressions of my magnetic field on the axis containing circular loop. So this is the initial formula I have, and I want to prove that it's a different cases. First of all, my case number 1 which I want to prove is that let's say first one is called as x equals to 0. It means that I don't have a such type of axis. It means that my current which is passing from here, and that x equals to 0 means this current carrying loop its x is 0, so it is having its magnetic field at this center. So I am proving this expression x equals to 0. So I am just first of all taking my formula that is suggesting me B is equals to mu 0 Ni into r square divided by 2 times of x square plus r square is to 3 by 2 where my x equals to 0. So my equation of a b on the x-axis, you can just say that x would be 0, so it would be mu 0 ni divided by 2r. So this would be r square 3 by 2, then square cancel out, 1 r is also cancel out, so I have left part in numerator is mu 0 ni and divide by 2r. Next case I have this is called as x is greater than r, or I can just say that x is very much greater than r. You can see that from the figure that we have taken such type of thing where x distance axis at this point P is actually larger than r. So we will use this data and placing this in the expressions. I can have dB of x integration is called as a b of x is equals to mu 0 I, and that is called as a 2, that is called as a x square plus r square will be 0, so that will be only just 3 by 2, and mu 0 I is okay. Instead of that we have 2 pi into r, and that is called as a r square. So I have taken that formula mu 0 I r square and the 2 pi, and then that is called as a 2 raised to some data available to me. So let's say I have just placed over here, that is called as a 2 pi, so I am just putting that over here 4 pi. So just placing this formula accurately, it will give me mu 0 upon 4 pi 2n pi I divided by our x cube. Why I have just taken that 4 pi? Because I want to compare this expression, otherwise that would be only a 2 will be okay for me. But what I want to just prove is that I have a m, that is called as a magnetic dipole moment, which contains formula m equals to ia. I is current and a is ampere, or if you have n number of loops, so for n number of loops our formula will become mania mi, m equals to ia or m equals to nia. You can just see that I have a pi r square available to me, I have current is available to me, and I have n is available to me. So this entire thing will be just replaced with the capital M. So my equation now will look like b is equals to mu 0 divided by 4 pi into 2m divided by x cube. Because I want to compare this expression, as I have told you, with the 2 kp by r cube, which is called as electric dipole moment. So you can just compare this. Instead of E we have a B, magnetic field. You have a K, that is called as our dielectric constant. You have a permeability of a vacuum, and 4 pi is also constant. You have a number, you have a electric dipole moment, that is called as a P equals to 2aq. You have a magnetic dipole moment which is called as ia, and that is called as x cube. So this is the equation where in initial part you can just see that I have just given such title that magnetic field on the axis. So it is related with the our formula of electric dipole moment on the axis. Yes, you can also derive that mu 0 divided by 4 pi into m upon x cube. This is called as the equation of magnetic field at equatorial line. So this is the equation of our magnetic field at equatorial line, which is also resembled with the our electric fields equation for the equatorial line. So these are the special cases. In this clip also we will discuss about the unit of a magnetic dipole moment. But first of all, let's complete the last case, that is called as our x equals to r. It means that we have such type of figure where previously we have assumed that x equals to 0, then x very greater than r, and now x is over here, means p point which was here, now it has been shifted over here, which is also having the same value with our capital R. So you can just say that our value will become like this one. So our value of x equals to r. So first of all I am just putting that expression mu 0 divided by 4 pi 2n pi and a square divided by a square. Instead of r you can just say a square and a square raised to 3 by 2. I have just taken radius my r, so my formula will become mu 0 upon 4 pi 2n pi r square and then r square plus r square. So this is only for the resemblance, because in all those clips I have used previously small a. So mu 0 upon 4 pi, you can see that our 2 pi and 2 will be cancelled out, our n would be left, so mu 0 upon 4 pi, then I have ni r square and r square is to 3 by 2, that is called as 2r square is to 3 by 2 and r square. Now and multiply by 2 pi, I'm just cancelling this one, so I have mu 0 ni upon 2 then r raised to 5 by 2. So this is the expression of my magnetic field at x equals to r. So now there is one question left over here, that I have just used this m is equals to ia. What is the unit and a magnetic dimensional configuration of magnetic dipole moment? You can see it is a current, that is called as our area. So it's a dimensional configuration, units contain ampere into meter square, and its dimensional configuration will be m0 L2, T0 and A1. So students, keep in mind, in exams they are asking that electric dipole moment and magnetic dipole moment, and you have to just find it out this formula for different type, and you can remember this formula for the three cases. And in exams they are asking for the current carrying loop, its central part, means on the axis, its equatorial line, x equals to 0, x is very greater than r, or x equals to r. So in this clip you will be comfortable with the finding it out equations of magnetic field on the axis, on the equatorial line, magnetic dipole moment's relationship with the electric dipole moment. So you can correlate this chapter with the chapter number 1, where almost all those quantities are having relationship less. I have just told you that E is electric field, same is the course for the B magnetic field. You have electric dipole moment P, which is called as a 2aq, and magnetic dipole moment which is called as a M, which is having formula M equals to Ia. So gradually comfortable yourself with the equations, and these all formulas we will use in examples. Thank you.